Okay, so today we'll be starting with a new module and a new chapter, and we'll be studying a new data structure. So the module of the chapter is tree, and in this chapter we'll be studying about tree. That what is the basic understanding of a tree? What are the different types of trees? Then what is binary tree? What are the different types of binary trees? Then what are the different operations that can be performed on a binary tree? Then we'll be discussing about binary search trees and then the implementation of binary search tree in C programming language. Then we'll be talking about the different operations that can be performed on a binary search tree. Then we'll be talking about the applications of binary tree, and we'll be talking about two important applications. One is called as expression tree, and another one is called as Huffman encoding algorithm or the Huffman algorithm. Then finally, we'll be learning about basic definitions of different types of trees, and into that we'll be learning a bit about AVL trees. Okay, that how the different rotations can be performed on AVL and what do you mean by AVL and so on. So this is basically what all things we are going to study in this module, in this chapter. Okay, so as you already know that when we started with the data structure, uh, we we had a discussion that a data structure is basically a way of storing or organizing a data into the memory so that it can be accessed efficiently. Okay? So that efficient access of a data is basically a crux of a data structure. Then depending upon application, then depending upon the suitability, we have this kind of data structures into which we can store our data or the way we can organize our data into the memory. Then we have seen that our data structure can be categorized into two. One category is linear data structure, another category is non-linear data structure. So in linear data structure, basically the relationship between the elements when how they are stored into the memory is basically linear, or there is some sort of sequence. So from one element you can go to the second, then from second you can go to the third, and so on. Okay, so for example, you need not have to come back here and there. So uh, the access, the accessibility is basically a linear in linear data structure. And in linear data structure, then we have studied arrays, we have studied linked list, we have studied stack, we have studied queues. So basically, we have seen four linear data structures. Now, this is basically a non-linear data structure tree. So this is the first non-linear data structure which we are going to study. And in general, we'll be studying two non-linear data structures. One is your tree, and second one is a graph. So this is the chapter module for the tree, and then the next chapter is basically about your graph. Okay. So the first thing is that a tree is a non-linear data structure. It means that all the elements are stored in such a way that when you try to access them, the accessibility is not linear. Okay, you need to come back to already accessed element or to already visited element. Then you can go to another element like that. Okay, so the accessibility is not linear in general. And let us see now. Let's start with what do you mean by tree, and what are the important terminology in tree, and so on. Okay, so we'll be starting with a basic presentation, a small presentation on this, and here we'll be studying a basic definition of a tree, and then we'll see how a tree is drawn, and how the tree is represented in the memory, and what are the important terminologies associated with the tree. So, definition of a tree. Now, please see here the definition may look like a little tricky, but this is one of the best definitions of a tree, and it is taken from a reference book. Horowitz and Sahni. So it's better to stick our understanding of tree with this definition. So what does it say? A tree is a finite set of one or more nodes such that. Now, a tree is a nonlinear data structure that is for clear. After that, we say that a tree is a finite set of one or more nodes such that there is a very first point, important point. There is a specially designated node called the root. Okay, there is a specially designated node called as the root. So, highlight. So a specially designated node, and that specially designated node is called as a root. Okay, this is important. So it means that our tree is going to have minimum, minimum one node. Okay, a tree is going to have minimum one node, and that node will be designated as a root. Even if a tree has more than one node, it doesn't matter how many nodes the tree has. Okay, more than one node, 5, 10, 50, 100,000, 10,000 lakh, whatever. More than one node, then one of the nodes is going to be designated as a root node of a tree. So in short, you can understand that it is the point from where the root starts. And if you compare this with our natural, it is a point, sorry, it is a point from where the tree starts. A root is a point from where the tree starts. Likewise, if you compare this with our natural tree, so we get the same thing, that a root is basically the point from where the tree starts. Okay. Likewise, in computer science also, for the tree data structure, there is specially designated node, and that specially designated node is called as a root, and it is a point or it is a node from where our tree starts. Okay. So it doesn't matter that how many nodes a tree is going to have, but it is for sure that the tree is going to have one specially designated node, and that one node is called as a root of a tree. That one node is called as the root of a tree. Okay. So here also you can see that a tree is a finite set of one or more nodes. A tree is a finite set of one or more nodes. Okay. Such that first point, there is a specially designated node called the root. Now see the second point carefully. First point is clear that in general a tree is a finite collection of nodes, and one of the nodes. First point is one of the node is specially designated as a root node. Okay. Second point, the remaining nodes. Now one node is designated as a root. If you got four nodes in your tree, so one node is designated as a root. So the remaining nodes, three nodes. If you got 1000 nodes in a tree, so one node is designated as a root node, and then the remaining 999 nodes. Okay, likewise. So the remaining nodes are partitioned into n greater than equals to 0 disjoint sets. Are partitioned into n greater than or equals to 0 disjoint sets. Okay, n greater than or equals to 0 disjoint sets. Fine. These sets are termed as T1, T2, T3, T4, so on up to T of n or Tn. Why Tn? Because there are n number of sets. Okay. So n number of sets, and they are termed or they are designated as T1, T2, T3 up to Tn. where each of these sets is a tree in turn. I repeat, where each of this set is a tree in turn. It simply means that if I divide the remaining nodes into, or if I partition the remaining nodes into n greater than or equals to 0. N can be 0, greater than or equals to 0. So n can be 0. So n greater than or equals to 0 disjoint sets T1, T2 up to Tn. So each one of this set is a tree in turn. So T1 is a tree, T2 is a tree, T3 is a tree, T4 is a tree, and so on up to Tn. So this is something like a recursive definition, which says that if you have a structure in which there are four nodes, one node is designated as a root node. So the remaining three nodes can be partitioned, can be divided into n greater than or equals to 0 disjoint sets. And each of these sets is a tree. It means that I can divide these remaining three nodes into three sets. So one node become one set, one node become another set, one node become another set. So three set. Each one of this set is a tree because this node, this set is having only one node that can be termed as a root. This set is also having only one node that can be termed as a root. This set is also having one node that can be termed as a root. Okay. Or for example, you divide these three nodes into two sets. This is my one set, this is one set, and these two nodes together one set. Okay. So again, the definition of tree is applied over here. So this is a tree. This set of two nodes is a tree. Okay. How it is a tree? One of the two nodes is designated as a root, and then the remaining nodes, that is one node, is divided into n greater than or equals to 0 disjoint sets. They are not joined, they are disjoint. Okay. So I have one set, and then this set is also a tree because it has only one node, that is a root node. Okay. So this is a recursive definition. And what does the definition says? Definition says that a tree is a finite set of one or more nodes such that, first condition, one of the nodes is specially designated as a root node. Then the remaining nodes can be partitioned, can be divided into n greater than or equals to 0 disjoint sets. Now why that equals to 0? That is very important. Why it is important? Because finally, when your tree has got only one node, so that one node is designated as a root node. So when this single node in a tree, there is a single node in a tree, this single node is designated as a root node. So there are no remaining nodes which can be divided into n sets. Okay. So the value of n becomes 0 because there are 0 sets. The value of n becomes 0. So that equals to 0 is also a very important condition. In fact, that is the condition which makes up the complete definition of a tree. Okay. So the remaining nodes are partitioned into n greater than or equals to 0 disjoint sets T1, T2, T3, T4 up to Tn such that where each of these sets is a tree. Each of these sets is a tree. Okay. Then we call T1, T2 up to Tn the subtrees of a root. What do we call them? They are the subtrees of a root. You have the root node, then below the root node you have the remaining sets, and each of this set is called as a subtree. They are under root node, they are called as a subtree. Okay. The moment we see the example, all these things would be clear. Now, you need to definition of a tree into your mind, and then we move to the next slide, which has the example of a tree, and then which has some important terminologies of a tree. Okay. Now, what we have seen there, What is a tree? It is a finite set of one or more nodes such that one node is specially designated as a root. So you are going to have a root into your tree. Let me draw that root. So here comes my root node. Now what is this circle and what is the value into that circle? Basically, when we draw a tree in computer science, so we represent the tree as a collection of nodes, and that is a part of definition. Finite set of one or more nodes. So then we draw the node in this circular shape. Generally, it is not mandated that your node should be circular in shape. For example, when we talk about list, so there we draw the node in the form of rectangular boxes. Okay, so there the rectangular box represents the node, and here this is something like a tradition or convention which we generally follow. So in most of the reference books, you will find this kind of notation. So here in trees and also in graph, when we show the node, we show it in a circular shape. So nothing special about it. This is just for illustration purpose. So in a list, we have the node in rectangular shape, and in this nonlinear data structures like tree and graph, we represent the node in a circular shape. That's all. So this is my node, one node, and then the thing which is written inside that node is basically the value of that node. Okay, so when we represent the node in a list, we draw a rectangular box, and inside the rectangular box, then we have the value or the data of a node, and then we have a pointer. Okay. Now here, uh, just to show a tree, just to show a graph, we draw it, and we draw it this way. So the nodes are shown in circular shapes, and then inside the node we write the value of that node. So basically here A, you can say that A is a value of my root node. Okay, or I can simply call it A, node A. I can also call it node A. Okay, so I can say that A is the value of a node, or I can simply call the entire node as node A. Fine. So this is my root node, and then I try to connect other nodes. A tree is a finite set of one or more nodes, such that one of the nodes is specially designated as a root, and then the remaining nodes. So I have an arrow operator, or you can say that is called as an edge. The arrow which is coming out of the root node and it is going to another node C is called as an edge. So we say that there's an edge between A and C, or there is a link between A and C. Okay, I repeat, there's an edge between A and C, or there is a link between A and C. Likewise, we can have few more nodes. So I got another edge, and then I got another node. Okay. Likewise, I can have few more nodes. So I got one more edge, I got one more node. Now if you see this tree, so into this tree, what we can say that my A is the root node, and then A has got two children. Now please see here, listen carefully, concentrate. I am saying the different terminology of tree. Okay, so root is one terminology. Then I am saying children, so it is also another terminology. The nodes which are directly under a given node is called as the children of that specific node. So there is a node A, and A has got now uh, uh, till this point of time, A has got two children, C and D. Then C has got one child, which is E. Okay, so this way, what we can see that this tree has got four nodes: A, C, D, and E so far. And my A is a root node. The remaining nodes C, D, and E, they can be further. They can be further divided or partitioned into n greater than or equals to 0 disjoint sets. It simply means that uh, I can have when A is designated as a root, so I can have this as one set T1 and this as another set T2. Okay. So into my set T1, I got two nodes C and E, and into my set T2, I got only one node, that is T. Okay. So we have now two sets T1 and T2, and what the definition says that each of this set is a tree. Now, if you see carefully, so yes, each of this set is a tree. For example, if you talk about this set, a T2 set, this is my T2, for example. So this set T2 is having only one node, and that node becomes a root of that set. Okay, that node D becomes the root of that set. So that is a tree. It doesn't have any further nodes to divide them or to partition them into n greater than or equal to 0 disjoint sets. Now, when you come to this set T1, this set T1, so into this set T1, what we have? We have two nodes, C and E. Okay. Now, these two nodes together, which is one set T1, is also a tree. How it is a tree? This C, this C can be designated as a root, and then the remaining nodes, which is only the E, can be then divided into n greater than or equals to 0 disjoint sets. So it can be divided into one set, and that set, which can be termed as T11. The entire set was T1, and then this inner set can be called as T11. Okay, so that set is going to have again one node, and that node can be designated as a root. So this way, now this entire setup can be defined as a tree. Okay, where this A is my root node, A is the root node, my A is a root node, and this is one set CE, and this D is another set. So I can say that this is my another subtree under A. A is my root, A is my root, this is my root, okay? And then under A, that is not visible now. And then under A, you got two subtrees. What do we have? We have two subtrees. One subtree is your this one, okay? And another subtree is this one. So this is my one subtree. This is my one subtree, and likewise this is another subtree under A. In the same line, when we talk about C and E, so C becomes my root node, C becomes the root node, and then E is a subtree under C. E is a subtree under C. Okay, so this way the definition becomes recursive. The definition becomes recursive. What is very important from understanding point of view, that when we talk about trees, so the most important thing, now this link is there, but it doesn't have any node. Let me have it, or let me remove it. So in this definition of a tree, what is very important, that you do not have any closed loop. The moment you get a loop, it doesn't remain a tree. What I mean to say, that if I'm having here also one node, one edge from C to E, C to D, like this. So there a circle is formed. The moment a circle or a cycle or a loop is formed, I repeat, the moment a circle, a cycle or loop is formed, then it doesn't remain a tree. It becomes a graph. What it becomes? It becomes a graph. Okay. So this is not a tree. I repeat, this is not a tree. Fine. Because it has a cycle in it, or it has a loop in it. So the moment you have a connection like this, or the moment you have a cycle like this, or the loop like this, then that data structure cannot be called as a tree. That data structure simply becomes a graph. Okay. So we cannot have this link, or we cannot have this edge. We need to remove this edge to make it tree. So now it is tree. Likewise, I can keep on adding the nodes provided the condition for a tree should be satisfied. Provided the condition for the tree should be satisfied. So I'm adding a edge, I'm adding a node, then I'm adding a edge, then I'm adding a node, again edge, a node, then edge, node, edge. So this way you can have a tree as bigger as possible, as larger as possible, depending upon your requirement. Now what we can see over here, that A is my root still. A has got three children, B, C, D. Is the voice lagging from my side? One or two students were saying voice lagging, then remaining few students, a few of the students replied them no, no, no. Okay, voice is going on properly. Huh? Thank you, thank you. See, this is important chapter, and this is a very interesting chapter, and it has got a lot of application. Basically, these trees and graphs. So, if you just search on them, you will find a lot of applications of trees and graphs. They are used almost everywhere. You can say in databases also they are used extensively, and in most of the application they are used extensively. Facebook uses them like anything. Twitter uses them like anything. So basically, almost all major applications make use of these data structures, and they are very important to understand from computer science point of view. So I request each one of you, please concentrate, please understand them properly. Okay. So this is my tree. As I again say you, then it has got so many nodes. So node A, which is a root, has got three children, B, C, and D, and then uh, there are other nodes like E, F, G, and H. Now, all these nodes, there are always parent-child relationship. So, A is the parent of B, C, D, then C the parent of E, then D the parent of F, then F is the parent of H, and so on. Then B, C, D, the nodes which are having the same parent are called as siblings. The nodes which are having the same parent are called siblings. So B, C, D are siblings. Okay, I repeat, B, C, D, and D are siblings. E and F are not siblings because the parent of E is C and the parent of F is a D. Okay, so E and F are not siblings. Then uh, let us see what do you mean by node basically. As I said, you already that in tree or generally in your non-linear data structure, the node is represented in a circular shape. So this is my node, and when I represent the node for the non-linear data structure, so I represent the node in a circular shape, and inside the circular shape, basically we write the value of a node. So if you see here that A is the value of my root node, A is the value of my root node. Likewise, B is the value of this node, C is the value of a node, D is the value of a node, and so on. So inside this circular shape, we specify the value. So that's why I have written val, the value of a node. And then after that, we have different edges which are coming out of a node and which are getting connected to its child. Every edge is uh, going to get connected to the child of a node. Okay. So one edge is coming out and it is getting connected to one child. another edge is coming out, it is getting connected to another child, and so on. So we can have n number of children for a specific node. I repeat, we can have n number of children for a specific node in a tree. In a tree, you can have n number of children, and that's why I'm showing it with the help of dot dot dot. So this is how a node is represented in your non-linear data structure, whether it's a tree or whether it's graph. Then next important terminology is your leaf nodes. Okay. Now, what are the leaf nodes? The way we have leaf in a tree, in the same way we have a leaf node in the way we have a leaf in a natural tree, the same way we have leaf node in a computer science tree. Okay. So in a computer science tree, basically the computer science tree is an upside down version of your natural tree. So if you visualize a natural tree, so you have the root at the bottom and then it grows up. But if you think of or if you visualize a computer science tree, so it has root at the top and then it grows down. Okay. It has a root at the top and then it grows down basically. Okay. So what are the leaf nodes? Leaf nodes are basically the nodes in a tree which does not have any child. So basically they are the terminal nodes. They are also called as terminal nodes. So they terminates. What they do? They terminates. Okay. So they do not have any child or they do not have any node further down to them. That's why they are called as the leaf nodes. So into this example tree, which nodes are leaf nodes? Can you tell me? Come on fast. Can you tell me which nodes are leaf nodes? B, G, H, B, G, H. BGH, BGH, right? BGH. Uh, Now I did some mistake, I think so. Let me see. Yes. So there's a mistake. I'm showing D as a leaf node, which is an absolute mistake. So sorry for that. Uh, your B is a leaf node. Yes. G is a leaf node. Yes. H is a leaf node. Yes. But D is not a leaf node. So this is absolutely wrong. This shouldn't be there. Okay. So I will remove that part. So that is not a leaf node. Absolutely not. Now, so B is a leaf node, G is a leaf node, H is a leaf node because they do not have any child and they are the terminals. Fine. Few other important terminology. One is called as the depth and it moves from root. It starts from root and it goes to the leaf nodes. Okay, I repeat, it starts from root and it goes to the leaf node. That is called a depth. So you can have a depth of a node or you can have a depth of a tree. I repeat, you can have a depth of a node or you can have a depth of a tree. So it starts from your root node and it goes to your terminal node or the leaf node. Okay, so the direction is this side. It will be starting from the root node and it will be moving towards your terminal nodes or the leaf nodes. Fine. Likewise, we have another important terminology called height. Okay. Now, how does the height grows? So basically, whenever we think of a height, so we check it from the bottom. And for a computer science tree, the bottom is the terminal node or the leaf nodes. Okay, so the your root is always at the upside for a computer science tree, and then the terminal or the leaf nodes are at the bottom. So when we talk about height, so we'll be checking the height from the bottom or from the leaf nodes, and we will be going up to the root node. So for the height, we'll be always starting from the leaf node and we'll be going up to the root node. So for the depth, we'll be starting from the root node and we'll be coming down towards the leaf nodes. And for the height, we will be starting from the leaf nodes and we'll be going up to the root node. Okay, you can find the depth of a node, you can find the depth of an entire tree. Likewise, you can find the height of a node, or you can find the height of an entire tree. So depth of any node can be calculated or can be just found, and likewise depth of an entire tree can be found, and then height of a node can be found, and height of an entire tree can be found. So what is then depth? So let me remove some parts. So nodes removed, leaf node also goes. Then the definition of depth. What do you mean by depth? So depth of a node M. If I think of any node in a tree, and let's call that node as M. So the depth of a node M in the tree is the length of the path from the root of the tree to M. Okay. Now see the definition carefully. The calculation of a depth is starting from the root as indicated in that arrow. Okay. So it is starting from a root and it is going up to that node whose depth we want to find out. And then in that path, in that path, whatever number of nodes we have, or you can say the length of that path is called as the depth of a node. Is called as the depth of that node. So if I ask you what is the depth of root, so what is the depth of a root node? What is the depth? A path is taken from the root node to that node. Okay. And whatever is the length of that path, that length is a depth. So what is the depth of a root? Yes, the depth of a root is 0. The depth of a root is 0. Okay. So if you see there, a 0 has appeared just beside the root node A, and that 0 is basically the depth of the root node. Because what is depth? What is depth? It is starting from the root node. You are starting from the root node and you are going up to a node whose depth you want to find. I want to find the depth of a root node. I will be starting from the root node and where I need to go to that node only. So I want to find the depth of a root itself. So I'm starting from root and I am ending to root. I'm starting from root, I am ending to root. So if you see the path from root to root, the path is 0. Root to root, the path is 0. Okay. If you see the path from root to say a node D, if you see the path, there's my pointer. If you see the path from this, from your root node, that is A, to your node D. I want to find the depth of D. Okay. So what I will be doing, I will be moving from the root node and I want to come to the node D. Okay. So the path from the root to D is this path. And what is the length of this path? Length is nothing, you can think of number of edges into the path. So number of edges in the path is basically the length. Okay. So the length is 1 over here. So the depth of my D becomes what? 1. See, I am using the color combination. So this, if you see here, how I am writing the depth, so the color of this, the color of this text depth is brown. So here also I am going for brown in the definition, and likewise in the number also brown. So this brown colored numbers are basically the depth of the node. So likewise, if I go for the depth of another node, say F, so the depth of F is 2, and likewise the depth of H is 3. Okay, depth of H is 3. Now, what is the depth of my entire tree? This way I can find the depth of any node. So the depth of A is 0, depth of D is 1, And likewise, the depth of C is also 1, depth of D is also 1. Depth of F is 2, and so the depth of E is also 2. Okay. Depth of H is 3, and so the depth of G is also 3. Fine. Now, you should understand that the depth of B, C, and D, depth of B, C, and D are same. Okay. And it is 1. Because they are on the same level. I repeat, they are on the same level, and that's why the depth is same. So the nodes on the same level have a same depth. I repeat, the nodes on the same level have the same depth. So the depth of B, C, and D are same. That is 1 because they are at the same level. Likewise, the depth of E and F are also same because they are also on the same level. The level is different as compared to B, C, and D, but they are at the same level, E and F. That's why their depths are also same. E and F are having the depth of 2. In the same line, the depth of G and H are same, and the depth is 3 because they are at the same level. So if you find the path from root node to this node G, so the length of that path is same to the length of the path of H. Okay, because they are on the same level. They are on the same level. So that is also understand, and that is also important to understand. So the level of the root is always 0. Then the nodes after the root are having the level of 1, and so on. Fine. So, and important thing, all the nodes on the same level have the same depth. All the nodes on the same level have the same depth. Okay. So that is the meaning of a depth. All the nodes on the same levels have a same depth. So what is depth again? Depth of a node M in the tree is the length of the path from the root of the tree to that node M. Now the question is, what is the depth of a tree? Can you tell me what is the depth of this tree? Come on fast. You should say. Yes, the depth of a tree is 3. The depth of a tree is 3. The longest path. You need to see the uh, depth of a leaf node with the longest path. I repeat, depth of a leaf node with the longest path is the depth of a tree. The depth of a leaf node with the longest path is the depth of your tree. So the depth of my tree over here in this example is 3, which is also the depth of H, a leaf node H and a leaf node G. The leaf node G and the leaf node H, they have the same longest path in the tree, and the longest path is a path with a value of 3. So the depth of my tree becomes 3. Let's see the definition of tree, and then we'll stop here. Definition of a height. Definition of a height. Height of a tree is one more than the depth of the deepest node in the tree. Height of a tree is one more than the depth of the deepest node in the tree. So the deepest node in the tree are G and H, and their depths are 3. So the height of my tree becomes 4. What is the height of a tree? A height of a tree is one more than the depth of the deepest node in the tree. So the deepest nodes in the tree are G and H. There are two deepest nodes. Why there are two deepest nodes? Because they are at the same level, G and H. Okay. So G and H are the two deepest nodes, and the depth of this deepest node is 3. So the height of my entire tree is plus 1. That is 3 plus 1 is 4. Okay. So 4 is the height of this example tree. 4 is the height of this example tree. Okay. So we'll continue in the next session, and I stop here because we are running out of time.